All right, Sriram, you ready?
Yep, I'm ready.
All right, let's get it started. First,
Okay.
so my first, do you want to introduce yourself?
Sure. I'm Sriram. I'm CTO with Zimbali Networks, and I'm super happy to be here. I think we're going to talk about Hashgraph today.
This is the humble genius, Doctor Sriram Nagaraj. He loves to undersell himself, and I'm going to let him do that today. Normally, I would give you his whole bio and resume, but for today, I'm going to let him be humble. We just get into the questions that we have. So,
Sure.
My first question is, what is Hashgraph consensus?
Okay. So Hashgraph, sort of as an algorithm, right, or as a consensus mechanism, I should say, is basically defines sort of the next generation of DLT technology. So DLT is distributed ledger technology, right? Decentralized. The entire notion of decentralization. And so blockchain was sort of first generation. Ethereum, actually now Ethereum with proof of stake is certainly second generation, and Hashgraph is, I would say, is a third generation method or collection of methods that achieve or solve this problem of consensus. And so, you know, way back when, we were using proof of work, which basically was like a sledgehammer approach of throwing huge amounts of computational power to verify, validate all of these transactions, and record them in a immutable ledger. And so Hashgraph basically solves the same problem without the need for excessive amounts of computational wastage. And so basically a hash graph is a decentralized ledger, and it's very similar to what blockchain or Ethereum are. So you store information securely, so cryptographically, and you verify transactions, and you sort of you do basically everything that a blockchain does. So that's basically what consensus is as a general concept. And so Hashgraph is this unique way of achieving consensus without the need for, well, actually, as a matter of fact, without the structure of a blockchain, right? So the structure of a blockchain is basically you have, a block of data which is encrypted, and then the entire block is validated, and then the next collection of transactions is bundled up into the next block, and the previous block is linked to the first block, the next block is linked to the previous block, and so on and so forth. And so that's why it's called a blockchain. It's a chain of blocks. But a hash graph, on the other hand, works on this principle of graph theory. So the entire data structure is not a sort of linked list or blockchain data structure. It's actually a graph data structure. And I guess we'll get into that in more detail.
Understood. Okay. So the hash graph is a more, well, one of the things that it is, based on what you said, is a more efficient way. Like it doesn't require as much.
Correct.
Okay. Excellent. So my next question is, we hear about gossip, the gossip
Correct.
protocol. What is gossip?
Okay. So again, going back to the previous question, so Hashgraph achieves consensus through this through the notion of gossip, right? And so basically, in common parlance, when you say gossip, you mean, you're talking about somebody, right? And somebody else is going to be talking to you about somebody else. And so you can imagine if there's a room of 10 people, and one person starts rattling off information about someone else or about themselves. Eventually, all the total amount of information that's being circulated is going to sort of reach some kind of steady state where at some point everyone's going to know everything about what everyone else spoke about, right? And so that's what we generally call gossiping, right? And how that information proceeds. And so here in the Hashgraph situation, it's very much similar. So what we mean by gossip is basically information that is transferred between nodes in the Hashgraph network, and that information, which basically contains timestamps of transactional information, previous hashes, and all of that wrapped up in with an encrypted signature. When that information is being transferred between nodes, that's what we call gossip. So it's basically the information exchange that's happening between the nodes in the Hashgraph network.
Okay, so the gossip is essentially the information transferred between the nodes within the network. So then, what is gossip about gossip?
Yeah, so that's a really important concept, and so maybe I can unpack that by means of an example, right? So again, let's go back to this situation where you have a room with 4 people, A, B, C, D, right? And so initially, person A has a bunch of information, right? So in the Hashgraph case, it's transactional information, but let's just say they just have a bunch of information. And so A talks to B and communicates all of their information with B, right? And then everything that A knows is given to B, right? And then B then has a transaction link with C, and all of the information that B has collected, which therefore includes everything that A told B, is communicated to C. And then C does the same thing with D, and so everything that C knows is transferred over to D. And so basically this continues across the network. And so now instead of people, A, B, C, D, imagine that you have nodes in the network. And so as this sort of information exchange continues across the network, you're having exchange, so therefore gossip by our definition. But not only is it information about what is the current state, right, of the network, but you're also, each node is transferring information about the entire history, right? And therefore, what is in the history? Well, the history contains all the previous states, and therefore that's the gossip about gossip, right? And so when at any given time, a node is going to be exchanging information with all the other nodes about not only stuff that it knows now, but it's stuff about stuff. It's stuff about its entire history of the entire transactions and also all of the previous conversations that took place. So you're conversing about conversations, right? And so that's the idea of gossip about gossip. And so every time you exchange information, it's not only the current information, but also the entire history.
Okay, and that's more efficient than proof of work and proof of stake.
Correct.
Okay, can you explain why it's more efficient?
Sure. So again, going back to the 2 main components in how Hashgraph achieves consensus. So this notion of gossip about gossip is one important way or one important, sort of component there. The other very important component is this idea of virtual voting. And we alluded to this in the previous Twitter space last week. So basically what's going to happen is, assume that, gossip about gossip has happened, right? So everyone's gossiped about, all the nodes have gossiped about all the other nodes. And so remember that I had told you that there's a timestamp that's associated with, say, a given transaction. And so this timestamp information is also passed across the network. And so what's going to happen is all the nodes, after gossiping has completed, the nodes are going to then vote, or virtually vote, about basically when this particular transaction was gossiped about, right? And so different nodes would have gotten information about a particular transaction at different times, depending on, remember, all of this is probabilistic, right? So if you have 10 nodes, and I'm node number 1, it's equally likely that I'm going to, first communicate with node number 7, and then node number 4, and then node number whatever, right? And so if I did this experiment again, with the same exact transaction, I would then have a different trajectory of how I'm going to be communicating with the different nodes. So because of this stochasticity, we have to have a way of aligning all of the different timestamps, right? And so basically what's going to happen is that the algorithm, and again, this is a design choice. There are various ways of aligning time, stamps, but the algorithm uses the median of all the timestamps. And so the median acts sort of as the result of the vote. So, all of the gossiping happens, and then all of the timestamps that have been received by different nodes are arranged, right, in lowest to highest or highest to lowest, and then the median timestamp is chosen as the winning, or whatever, the unique timestamp for that transaction. And so you align, and again, all of the information is bundled with this timestamp. And so once you've picked the median timestamp, you've basically obtained consensus, because all of the nodes have this information, and this sort of mechanism by picking the median timestamp is how you ensure uniqueness. So once you have existence and uniqueness, you have a unique solution.
Okay, and you mentioned that the trajectory is stochastic when you're talking about how it's a kind of a probabilistic
correct
system. Can you just briefly explain what that means?
Sure. So basically, imagine you had a random experiment, right? And so, could be the roll of a dice, right? And say, one side is heavier. Say the dice with the face 5, the ordinary 6-sided die, but the side with the face having 5 is heavier. Say, now you roll this die, and then you roll it often enough, you're going to have different outcomes. But eventually, because the face corresponding to 5 is heavier, you're going to have a difference. So it's not going to always favor all the faces equally. It might favor 5 more because it's a heavier face, right? And so, but every particular roll is going to be different. But in the long term, you're going to converge to the probability of you getting a 5 being higher. So that same example works here in a certain way, because the node communication, so the way in which a node picks the other from the list of the other nodes to gossip with is kind of random. It's not like node 1 always picks node 5 and then picks node 7 and then picks node number 10, right? And so on and so forth. It's going to pick a random node to gossip. I mean, that's the whole point of gossiping, this randomness, right? But what the theory shows is that eventually, after enough time passes, so in other words, in probability, so with probability equal to 1, you will attain consensus. And that's a provable mathematical result. And so when you say with probability 1, well, you could say if something happens with probability 1, doesn't that mean that, it's for sure going to happen? Yes, it is true that it'll for sure happen, but the difference is that something is going to definitely happen, but you do not know what path it takes in order to get to that final destination. Do you see the subtle difference? So if something is absolutely certain, you know that you're going to reach a particular destination, but you also have 100% confidence in the path that you take to reach that final destination. So in this case, you know that you're going to achieve consensus, but the exact path might be different at different, roll of the die, so to speak.
Right. So it's akin to how, like, if you flip a coin a zillion times, like, eventually you're going to get to 50-50 in terms of and then okay, so you don't know exactly how you get there. That's unpredictable. What's predictable is the outcome.
Correct.
Okay. Yeah, I stumbled through a stochastic calculus class in college that I had no business being in, and so I understand a little bit of what that means, enough to know that it merited further explanation for folks who are listening. My next question is, go ahead.
Yeah. So I just wanted to reemphasize that. So because you know that it's going to, happen with probability 1, you may achieve consensus. So the time to achieving consensus has sort of like an upper bound, but within that upper bound, you may achieve consensus quicker, faster, or slower, but you know that it's not going to take forever, right? And so when we eventually talk about the differences between blockchain and Hashgraph, I think that's going to be another important distinction. But I guess we'll get to that.
Awesome. Yeah, before we get to that, I wanted to ask, what exactly does asynchronous Byzantine fault tolerance mean? What is that?
Okay, so that I need to go back a little bit in the history of distributed computing. So bear with me. I'm a big fan of history because I think history teaches us a lot, especially in the history of science. So bear with me for a few minutes. So this entire problem that blockchain, the hash graph, all of these different approaches, the thing that they're trying to address is the following problem in communication, right? And so what the problem is that, let's say you had a bunch of nodes. So in other words, just think of a bunch of people, so say 10 people, who are communicating with each other. So they're sending messages between one another. And there are two types of problems that might occur in this. So just imagine, each person with a loudspeaker just talking to each other, right? So there are two different types of problems. One is that one person's loudspeaker might just be randomly off, so no one else can hear them, right? So this is one type of fault in the network where, one node just completely breaks down, right? This is kind of a benign fault. It just randomly happens that one of the nodes breaks and is no longer able to communicate, right? So that's one. The more sinister type of fault is when one of the nodes acts in a malicious way, meaning it's sending out wrong information, or it's been compromised in some way that it's the information that it's sending is no longer reliable. And so this type of a fault is called a Byzantine fault. It apparently has some, I don't know, I'm not an expert in Byzantine history, but apparently there was a war in which you had a bunch of generals and they had to all give the same type of order to their soldiers in order to successfully complete a campaign. but it was known a priori that there are a handful of generals within the collection of all generals who are actually working against the overall collection of generals, and so these generals were called, for whatever reason, Byzantine generals. And so the problem is basically the same. How do you still communicate? So again, in the historical question, it was like, how do all the generals still give the same order to their soldiers in spite of having a handful of renegade generals, right? And so because that problem is kind of similar to this, these kinds of faults where you have malicious nodes are called Byzantine faults. And so you had asked the question, asynchronous Byzantine fault tolerance. So I've explained to you what a Byzantine fault is. And so way back in the late 90s, early 2000s, there's this one, and I encourage you to Google this guy. His name is Leslie Lamport. He's a very famous computer scientist who was kind of like the forerunner for a lot of the fault-tolerant computing, distributed computing stuff. So they came up, he and other researchers came up with various algorithms to solve the benign faults, meaning just randomly, nodes shutting down. So how do you communicate in an environment where some of the nodes just randomly shut down? And turns out that that's actually not a very difficult problem to solve. And there are actually mathematical results that tell you how many such nodes can you tolerate. So how many nodes breaking down can you tolerate before communication becomes totally impossible? These are called, in mathematics, they're called impossibility results. And then Leslie Lamport went on to solve the Byzantine fault-tolerant problem, which is a much harder problem, using a different type of algorithm. But the whole point is that these types of solutions to fault tolerance are not scalable, in that if the number of, or I shouldn't say not scalable, they scale pretty badly as the number of nodes increases. And so this is where Satoshi Nakamoto played a huge role in the early 2008, when the idea of blockchain was sort of unveiled, because it solves the Byzantine fault-tolerant problem with appropriate scalability guarantees. And so basically, we're solving a problem that's already been solved, but then in a much more efficient manner, right? So that is how blockchain came to be, right? So again, I don't want this to be a talk about blockchain, but then you have this notion of proof of work, and so each node needs to do the proof of work in order to for its results to be validated by all the other nodes, and then that's how you believe this node. And so if you were a Byzantine node, then you would actually have to do increasingly infinite amount of work, or increasingly higher amount of computing work, in order to keep up being a bad actor as the blockchain proceeds, and that becomes infinite amount of work at some point. And so that's how you mitigate against renegade nodes in the blockchain solution. So that's basically Byzantine fault tolerance. And so now I have to explain the asynchronous part. So what Hashgraph does is, also solves the Byzantine fault tolerant problem, but because each basically Hedera node will, as I mentioned earlier, eventually reach a point where it knows for sure that a network has reached consensus. So in other words, there is this time component here. And so, regardless of where you begin, you know that eventually you will, with probability 1, achieve consensus. And so that's sort of what it means to be asynchronously Byzantine fault tolerant. So,
no matter where you begin,
correct,
you will, with probability 1, reach consensus. Okay, I got it. And that's kind of similar to what we were talking about earlier with the probabilistic nature. And so my last question for you today, Dr. Nagaraj, is what is the difference between the hash graph and a blockchain?
Gotcha. Okay. So we've addressed, or we've highlighted a few differences. So one of the things is that the data structure of a blockchain, again, is you have a block of transactions which has been validated and cryptographically, secured, and then once that block has been mined, it is attached to the previous block. So in other words, the data structure you want to have in mind is basically one block tied to another block tied to another block. So it's like this linear kind of data structure, and you can't insert a block in the middle, right, of two blocks. You've always got to append a new block to the end, and it's also immutable in the sense that once a block has been published, there's no way to undo the contents of a previously mined block. So it's got this very linear append-only structure. But it, again, from a functionality perspective, it is Byzantine fault tolerant, but it comes with this structure. And the reason for this structure is because of again, the overarching mechanism by which consensus is achieved in the blockchain case, where you have these nodes that are doing all of these mining, and then once a miner gets the right answer, that miner's transactions are bundled into a block and attached. So because the data structure of a blockchain is it is the way it is because of the consensus algorithm. However, in the hash graph case, as the name suggests, it's not a blockchain; it's a graph. And the hash of the hash graph is because it invokes cryptographic hashes in order to do all of the security stuff. But it's a graph. So what is a graph? Well, a graph is basically a collection of nodes which are connected with one another, right? And so you have, think of, a bunch of dots and a bunch of dots being connected to each other, but they don't have to be connected in a linear fashion. In other words, you could have loops, you could have various nonlinear kind of relationships between the nodes of a block, of a graph, rather. And so the gossip about gossip is the reason why you have come up with this graph structure, because since you randomly gossip so if you were a node and you are connected to another node that you gossip with, well, you could gossip with any, as we mentioned earlier, a random collection of nodes. And so that doesn't have to follow a linear path. And so the data structure that underlies the consensus mechanism is naturally that of a graph rather than that of a blockchain. And so from a data structure perspective, they're totally kind of different. Now, in terms of functionality, there is no proof of work per se in the hash graph regime. All you have is this two-step procedure. You have gossip about gossip and then virtual voting, and boom, you achieve consensus. So in terms of efficiency of achieving, asynchronous Byzantine fault-tolerant consensus is much faster. It's much more efficient with the hash graph approach rather than the naive sort of proof of work approach, which A is time consuming and B is obscenely wasteful. I mean, as a computational scientist myself, I shed tears of blood when I see all of this compute power being wasted for like complete silly purpose, in my opinion. Like, who cares like what this nonce is to achieve? Yeah, I mean, this is just total number crunching for the sake of number crunching. I mean, it's a total waste of computational resources. And so, from an efficiency perspective, hands down, they're not even in the same league, I think. So that's one. The second thing is, as we mentioned earlier, these probabilistic guarantees. So if you guys are familiar with this notion of a set, sort of in the blockchain case, if you do have a renegade node, you kind of, in order before you achieve consensus, you have the possibility of sort of two different paths being started in the same blockchain, and then one of those chains would die off because for whatever reason that chain of transactions is not validated at some point. And so you have this possibility of, or rather, you'd have to wait for a few more blocks in order to a posteriori, sort of like after the fact, validate a previous block. You know what I mean? But that doesn't happen in Hashgraph. It is, once consensus happens, it happens. I mean, it's over, right? And so you have both efficiency in terms of time and also efficiency in terms of resources with Hashgraph versus blockchain, not to mention the differences in data structures.
Okay, so the proof of work system that popularized by Bitcoin is a lot of wasted compute power.
Yes.
Because of that like linear append structure, and then the gossip about gossip combined with the virtual voting is much more efficient. The underlying data structure is like that of a graph as opposed to like a blockchain. Okay, absolutely awesome. Well, I don't have any more questions for today. It's past our usual closing time. Just want to say first that in a future episode, we're going to directly address some of the Hedera Salt, let's say. We all know about the Hedera Salt bot, which is a very, almost like an entertainment account at this point, the way that it interacts with space. But we're going to directly address Hedera FUD, Counter FUD, and Counter FUD, that historic series of Medium articles, and also Guy Osiris Coin Bureau video about the Hashgraph, the negative. We're also planning out an episode with Benito Fernandez, who is the CTO of the Whisper Company. The Whisper Company is doing cutting edge research and development in identity protection and cybersecurity. Zimbali and Oro is a proud partner of the Whisper Company, and we will be using their post quantum encryption to secure our wallets. And so we'll be having Benito Fernandez speak in a later episode, the CTO of that company. Before we close, is there anything that anybody in the audience would like to say? Just request to come up, and I will give the floor, or anything that Sriram you'd like to share in closing with the people.
Yeah, no, I think this was a great section, and look forward to the next one where we can dispel some of the myths associated with the Shrek algorithm. I hope today sort of was a useful sort of session where we sort of got all the terminology under our belt, and then next time we can have a nice discussion about some of these criticisms that people have raised.
Absolutely. Well, last thing for me is for the folks who have made it to the end of the room, we do have a POAP commemorating the space. I will DM you the link to claim that POAP. You have to do so by Thursday, when our next space will be taking place at noon Eastern time on Thursday. So 4 hours before this space started, if you're trying to figure out the time in your time zone. That will be the last day to claim that POAP. So I'll be sending out those links right now. And our final word, as always, if you want to get rich, go alone. If you like to build wealth. Go with World. Thank you very much for being here.